So you mean in a crossfit? So actually there might be some overlap.
That's a huge trenches. Oh, there's one I really want that. I mean, big garden house. I'm sure it's all shoots the mix.
Yeah, so
well, you can't go crazy nice and Boris. Many of the natural ones. No, but that also depends on nice time to come with
I mean, that's what they did. So I like it.
Yeah.
The funny thing is that shortly after is that you don't have enough people to find the platform offering low maintenance. There's a certain goal which is
Yeah, so that's what it is. In the letter, they said, they can't really projects that are along the funded administration, you're going to shuffle people around. I probably will help in the next year they'll hire again, you know, all the different strategic areas.
I think that the problem is that every company there's certain sort of pieces of knowledge that have nothing to do with what they're exactly working on. They're more like it's and they just go away. I think some of the like is because we have to figure out the and of course, we're playing. One of the things so that if you read it on the wall, and then basically, but you cannot so somebody made a mistake and ended up and Savannah
Yeah, so there's Francisco.
Yeah, I know. You're collaborating on
So the only reason I know that is she randomly saw me at like quiet thing that we did, and she was like, "Oh hey, you proof this and to play." Yeah.
That's the
Hey, good morning everyone. Welcome to the morning session. So I think we have to start, try to be on time. As you can see, I'm Jeff Beach. Actually, Jeff had to go home, so I'm standing in for him. So we have in the morning 4 presentations, 2 before the break, 2 after the break. Every presentation is half an hour plus questions. And so we start with the local. So from the Salabas, and the speaker is Boris, and the work from was done by young country. So please.
Thank you very much.
First, good morning, everyone. Everybody says good morning. So my name is, as I said, Boris Maiorov. I'm going to be presenting some resonant ultrasound spectroscopy work we did in MnSi. When I say we did, it's Young Camp who did. And here's a list of collaborators, but I would like to highlight the work by Young Camp that it was amazing, not only in the quality, but in the amount also. And I'm only showing one part of the job that Young Camp was able to do. So I'll start with some bad memories. Back in the time in Argentina when I studied physics, first experiment I had to do in experimental physics was measuring the young modules. And it was a very painful experiment. Not itself for the measurement, but for everything that was around. I think they had the original Thomas Young experiment that they brought it to Argentina. And it was really old, really painful. Since then, I had some sort of an allergy towards elasticity. Until a couple of years ago, when I was offered the possibility of learning this technique from Albert, and I said, why not? Anyhow, but the idea of elastic measurements is that usually you have, let's take these young models. You get the ratio of basically the force over the displacement. So what you do in this case, you put different weights and you see how this wire elongates, and that gives you an idea of how strong it is, how elastic it is. So something like a rubber band will move very easily. Something like tungsten will be much stiffer. Now, these type of measurements are fairly difficult to do. It's difficult to do it correctly, and usually you get into problems where the excitation you're doing, let's say the weight, goes into the elastic, or you start deforming your sample. So in order to get a little bit more insight into elasticity, I will show you one of the things we do. So why do we want to study elasticity? Well, the thing is, when you measure elastic constant and you measure elasticity, you can go learn both from the very, let's say, pure science, atomic potential, structure, etc., and also it's very useful for things like engineering. If you want to know how hard material is, if it will withstand a certain pressure, etc., etc. So it allows us to go from one way to the other. Elastic modules are a fundamental thermodynamic susceptibility. So it's a second derivative for the free energy. So what I'm measuring is sort of like a specific heat, if you want, but with symmetry information. So a simple example is you just have a simple interatomic potential. The mean position will give you the volume. So as you raise the temperature, your material expands, and the depth of this will give you the energy. So this is translated. So a thermal expansion, you increase the temperature, the material will expand because basically they are further apart. And then the same thermal excitation will soften the material. So typical bulk modulus as a function of temperature will be flat below temperature, and then it will decrease linearly at very high temperature. Now, you can go a little bit further and you compare two different materials. Compare both are metals, but the problem is, or the interesting part is, beryllium has a very different type of bonding. It's a hexagonal that has very close bonding, and then you get very different temperature dependent. This is characteristic of the divide temperature. The slope is characteristic of Dyson parameter. So you can get a lot of interatomic intrinsic information by measuring elastic constant. Now, interesting things happen when you measure negative thermal expansion. And you would imagine if the material is shrinking as you get higher temperature, your moduli should increase because you're getting atoms closer. Well, what happens in most of the material is that when you heat, and I'm showing some examples we measure in the scandium chloride. So this is, you have a rhomboid, and when you heat shrinks, but because these things are rotating. And because it's rotating, you have other interatomic potential, and what you measure is actually a softening. You don't see something that is getting stiffer, but you also see something like you would expect in a standard metal, that you can see softening. And what it's telling you is that in reality you have some free parameter inside that you're not seeing. In this case, is the rotation, this free ring parameter. And this free parameter can be electronic, can be magnetic, can be anyhow. But so just by looking or measuring the elastic moduli as a function of temperature, it can tell us a lot. Same thing with the superconducting transition. In this case, I'm comparing YBCO, cerium colloid 5, and plutonium gallium. And this particular guy has a very different type of transition. As you can see here, it goes down and then goes up, which is something that also happens in MnSi. And this is because we have balanced fluctuations. And this only happens in outside the plane and not in the plane. So why do we want to do this with Skyrmion? Well, a couple of years ago, me and coworkers showed that by measuring sound speed, that they could see the changes entering into the Skyrmion phase. And so so what they see is you start at zero field, you see the splitting. When you have a cubic system and you put a magnetic field, this breaks the symmetry. So you have one C, in this case is C11 and C33. C11 is the compression of vortices once against vortices, one against each other, and C33 is the compression perpendicular to the direction of the magnetic field. And when you see that, you see the split. Typically, you can see the transition from the helical to the conical, and then in the Skyrmion phase you see stiffening, and you see softening depending which elastic constant you see. In the C11, the one that measures the one Skyrmion against the other, you see a stiffening, and then along the field you see softening. And so the way you do it, a typical pulse echo technique to measure elastic constant is you have a pulse generator, and then you send a pulse into a sample. To make this, you have your piezoelectric transducer that is blue, your sample, and then you send your sound wave, and you basically hear the echo with the same transducer. This has a lot of good things and some drawbacks. The good things are you can make this measurement really fast. You can have, so let's say if you're changing your magnetic field, or you can change rapidly your temperature, and you can get a lot of data. The main problem is that getting a very good blue is complicated, particularly if you want to do different temperatures, because you have to make something that all the sound is transmitted back and forward. But the more, I would say, the more cumbersome part is that you need a sample for each elastic constant that you are measuring. So if you have a single crystal with low symmetry, you need several single crystals. So particularly if it's a material that is new and has one single crystal, you want to measure, let's say, 6 elastic constants, you cannot do it. The other thing is, usually the sample has to be a bar shape, so actually longer in the direction that you're measuring. So you have a particular geometry restraint. And that's why we use resonant spectroscopy. A couple of years ago, the first time I heard resonant spectroscopy, these things came to my mind. Resonant, you have something like this, ultrasound, this was for me ultrasound, and spectroscopy is fairly easy. It's a little bit more simpler than that. There are no babies involved. I know. Anyway, so the basic technique is actually really basic, and that's the beauty, and very simple, and that's the beauty of this technique. So you have basically 2 transducers, piezoelectric. In one you put an excitation, a signal that you're going to be sweeping in frequency, and the other picks up. And that's it. That's all you're expecting. Very simple. And the back already has. And when you hit a resonance, a mode, a resonance of your sample, you see a peak. Now, just think of a string, those who play guitar or violin or a trumpet or a triangle. We all are able to play triangle, I think. That's what I measured. We play the resonance. And the longer, and so there are two things you measure: the frequency of the resonance and the Q of the resonance. The Q of the resonance is how long does this resonance exist? Or if you have a resonance peak, how sharp this is. Now I'll show you a little bit in a second. So but this is what you measure. You measure the voltage, the real imaginary part as a function of frequency. And each one of these peaks depend on the elastic constant of the material. Now, it's fairly easy, and each one of these peaks depends on one of these modes. These are simulations of displacement of a Faraday pipe, and this is the first mode, this is the second mode. So usually the first mode is a shear mode, so you have something that goes like this, and then you have a mixture of different elastic modes like in each one of these frequencies. So one important thing to have to remember, the wavelengths I'm having here are basically of the length of the sample. So this is macroscopic. You can think that the excitation is almost DC in the way of the wavelength length towards, let's say, the skyrmion or the atom's length. The other thing is that what I will get here will depend both on the geometry of the sample. So just think of the string of the guitar, you make it shorter rings higher, that is the same string. And it will depend, of course, on the elastic constant. It's not the same thing to have a metallic string than to have a plastic string. My daughter is learning guitar, so sorry. Anyhow, so the other thing is that once you have elastic constant, it's fairly easy to calculate the position of the peaks, the forward problem. So you know what your elastic constant, you can see, okay, I will have a resonance here, we'll have a resonance here, have a resonance here. Now, the inverse problem, having the resonance and then getting, let's say, 6 elastic constants or something like that, it was something that was only solved in the late 80s. And at the time, it took considerable computational effort. Now you can do it in your PC in half a second, not half a minute. So now the problem of starting with the position and getting the solution is much simpler. So this is how we do it. We use a program that needs basically your geometry and your symmetry. This is very important. It's not the same to solve the elastic problem of a polycrystal where you have 2 elastic constants than to solve it in, say, an orthorhombic where you have 9. In this case, we have in a zero field, we have a cubic system with 3 elastic constants for MnSi, and then when we apply a magnetic field, we break it into a tetrahedral symmetry. One of the cool things of solving this problem is that this is the number of the peak, and this is the experimental frequency, and these are the component of each of the elastic constant. So let's say if we take number 3, you will be given mostly 3 or 4. These are basically depend only on C11. And this gives us a very practical way to basically, we can track on frequency, and it's going to tell us a lot about what that particular elastic modulus is doing. In this case, C11. And we are going to do that in order to make the experiment easier. So basically, Cij depends on the square of the frequency, so variations of Cij will be basically 2 times the variations in frequency. This is the systems that we use. We use 2 types. One is called a cantilever, the other is basically a piston. The reason you have something that needs to move in the top is that the sample expands and you want to keep track of that. This is actually the sample the system that we use in the experiment I'm going to show. And the reason it's all metallic is that these systems can also be used at high temperature. So we can go up to whatever our system can go. In this case, we can reach 900K easily. but of course in this case we went to 30K. And if you just want to do things at low temperatures, then what you do is you build your system with plastics and balsa wood and things like that. So this is the MnSi, this is the experiment we want to measure. So standard things, triple R or around 90. We see the transition, susceptibility without and with field, which shows the presence of Skyrmion phase. Here is the susceptibility at different temperatures as a function field with the clear presence of the Skyrmion phase. One thing I want to point out is that we also measure Hall effect. We do not see a topological Hall effect in these crystals as was shown by the group of fire. So there are some difference between these crystals and the crystals that say fire group. Now this is the resonant ultrasonic spectra. So what we do is we measure as a function of frequency. We index each one of the resonant peaks. And then, let's say from 24 peaks that we have indexed here, we are able to get the elastic constant. So here I'm showing C11, C12, C44, and C star. And you say, why? I just told you that we only have 3 elastic constant, and I'm showing you 4. Well, the way you do it is, this is the compression along the 1, 0, 0 direction. This is the shear, this is the pure shear in the 1, 0, 0. And C star is actually the physical quantity, is the shear along the 1, 1, 1 direction. So it's what you would get if you measure sound speed in the 1, 1, 1 direction. And this is why people always calculate C1, C star. And what we see is that at the transition, we see a huge softening of the C11. And what this is telling us that this transition has to do with orbital fluctuations, if you want, and not pairing, lateral pairing, as you could say. If you have transition, a hardening transition, you have shear pairing between the orbitals, and you don't see a big thing here. And this is consistent with measurements done in MnSi ultrasonic measurements back in the 80s. And here I'm showing new results, but this was known for many years. The other thing that I can say is that if we look for breaking of the symmetry between ETC, we have clear evidence that we can see how the symmetry is breaking when we get into the helical phase. I don't have time to show the details, but let's say we solve this as a tetragonal system, all the tetragonicity is constant at higher temperatures, and then we see how it evolves as we go below ETC. So this is a very sensitive technique. Now, this is with magnetic field, and we do 2 types of measurements. I'm basically showing the tracking of one of the frequencies, both as a temperature, and the other thing that I'm showing here is the attenuation. As I said, the attenuation is basically how thick, how wide the peak, the resonance peak is. The wider the resonance, the more the attenuation you can think of. If you have a piece of epoxy or a piece of plastic, this will not resonate. Or you have something like that, resonance will be really, really wide. And that means that you have some sort of absorption into your sound. So we can see the first transition, and also we can see the transition into the Skyrmion phase as this will live in the frequency as a big peak in the attenuation. We can also do field dependence of the frequency, and here the presence of the Skyrmion phase is way clearer. You can see how, and this is again a frequency that depends on C11, so we see something that stiffens, and then this gets smaller as we go to lower temperatures. And both the place and the amount of change of the frequencies are consistent with the previous results by me and Tal from a couple of years ago. Now, we can make a very good phase diagram of this, but this is not what we want to do. What we want to do are 2 things. One, to explore quantitatively the elastic constant. The good thing of getting the resonant ultrasound is that we can get all the elastic constant, and with that we can do comparison of the numbers that we are getting. In the pulse echo, what you have to do, let's say this is your sample, you measure field like this, but then in the same configuration, let's say to measure C11, measure C33, you do like this. Then you're changing your Dmax 5. And then in order to measure C star, you make another sample. So sample to sample variation, sample configuration variation, all these things are going to give you errors, but we can do all in one sample. The other thing is that we want to relate the thermodynamic aspect with the dynamic, with the critical current properties. And borrowing, for those who know, this is a picture from Blatter review, this is for vortices, but the nice thing of all these theories about thinning is that as long as you don't say what this line is, you can have the same models of that. You have a linear object that is elastic interacting with a thinning center, in this case, our thinning center. So a lot of what we know from thinning of vortices, we can apply. Remembering that what's the true nature of the Skyrmion phase. So here are some of the results. I'm showing you C11, oh sorry, I didn't show. So this is C11 and C33, C12 and C23, and also the C44, the shear mode C44 and C6. So immediately you can see that both in the pure compression and the pure shear, you can see the Skyrmion phase. The other thing you can see is that the values of the stiffening, let's say in C11, are much larger than the stiffening in C66. And this is important because one of the computational calculations of the stiffening of the Skyrmion says that you should have pretty much the same C11 than the C66. And this is actually very different to what you will get, let's say, in a vortex lattice where the C66 is much smaller. Basically, you can break vortices very easily by shear. Skyrmion should be much harder to break laterally. That's the C66. Now, so this raises a couple of questions. One is that is this little jump that I'm measuring here or here really the elasticity of the sun? I'm measuring, this is the elasticity of the Skyrmion system. I'm measuring the whole elasticity. I'm measuring the whole sample. So actually what I'm measuring is the coupling between the Skyrmion and the ionic lattice. So we need more calculation to really see how the Skyrmion lattice couples to the real lattice. The other thing that also tells us is we calculate C star, and as I told you, that's the pure shear in the 111 direction. This is in the 110 direction. These, if we have a hexagonal symmetry, should be the same than the C66. So the jump here is actually an order of magnitude bigger than in the C66. So this is telling us that we do not have an hexagonal symmetry. So the symmetry of the Skyrmions it's not winning against the lattice symmetry, at least in terms of elastic modulus. We can go even further, and now we put current at the same time that we measure the resonance. So Yang was able to put leads and put current and not destroy everything, and at the same time being able to track the frequencies. So here I'm showing C11 frequency. It's 93% C11, and what we did is track the jump, the stiffening jump is delta F at different temperatures for different current. So here, let's go at zero current. In both cases, you see at all the temperatures, we see a jump. And depending on where we are in temperature, closer to the end of the phase diagram or in the middle, we see this jump bigger. And this is basically the stiffness of the lattice as a function of temperature. But now we apply current. And what we see is that basically it doesn't change, so it's 0 and it has a bunch of different currents. At 0 and 9, you basically don't see much difference. Only when you get around 10, you start seeing this going down, and then by the time you get to 12 or even 11, this is totally flat. And you can see that the same phenomenology happens at all the different temperatures. Doesn't change until you get to the critical current, and then it becomes flat. You can see it a little bit better, or I can see it a little bit better. So what I did is I just took all this data and just set everything to 0 at 1 kilohertz. And this is the data, same delta F frequency as a function of field. And you see 0 and 9 are basically the same. So we put 0 current for 9 milliamps, and the stiffening of the system has not changed. However, when we get to 10, 11, 12, this goes down really drastically. Here I'm plotting the results of basically delta F as a function of current, this high as a function of current, for 2 different temperatures. So this within our resolution is flat until we get to, in this case, it's 20, 21, 22 milliamps, and in basically 1 milliamp, this goes to 0. And the same happens if you go a different temperature, but a much different current. So we see 2 things. One, we can erase the stiffening. The coupling between the skyrmions and the lattice can be erased by current. The other thing is that it depends in temperature. It depends on where you are in your skyrmion lattice, you will have different values. So what we can do now is to compare the stiffening and the critical current as a function of temperature. The first thing we see is that this is different to what you expect if you have a critical current that only depends on the elasticity. So if a critical current only depends on elasticity, then basically JC should be an inverse of this. Here it should go down and then it should go up all the way. And we see that happens in this region. This goes down, so inverse of this, and then it starts going up. So this critical current we are measuring does not depend solely on the elasticity. But the thing I have not said is, why is this critical current? I talk about decoupling. That's very clear that we have skyrmion decoupling to the lattice, and our basic assumption is, well, we know that when you put current, the skyrmions will start to move. But the value and the temperature dependence that we have, the values are much lower than the values that say measured by a critical current using a topological effect. We're around 1 milliamp, we are around 50 kiloamp, so it's much lower. And the temperature dependence is also different. So the first thing we thought is, well, maybe it's this ultrasonic excitation that we're doing that is changing the critical current, increasing, similar to what we saw on Monday with magnetic field that is happening. Now, this same type of phenomena happens also in vortices. Actually, this is part of my PhD thesis, where you can put AC current or AC field, and you can change the critical current as a peak effect in superconductors. So we did this with 2 types of amplitudes. And here is making twice the amplitude, and we basically get the same value. We also know that this is not heating, because if we were going to measure below the skyrmion phase, we should have a critical current. If we are going into the skyrmion phase, and we don't see that for some other reason. So the other thing is that we see something that is really abrupt, and we don't see something that goes slowly. But I think that abruptness can be explained by averages. We were discussing Marcus the other day. Anyhow, so to summarize, we can see skyrmions, we can determine the elastic constant, and we can determine the changes that they do into the elastic constant. We can see also inside of the fluctuation dynamics that I didn't have time to go today. The changes in delta of C11 are much bigger than those of C66, and also we can induce decoupling with critical current and study temperature. Thank you. Yes and no. So this is a bulk thing. You see a bulk signal. Now, people have measured thin films by making substrates very, 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 very thin, and then, let's say, if you measure changes, you can make some modeling of a two-phase, and you can get the elastic constant of the change. Or you can do just qualitative changes and say, well, you know, I see the change here and can track a phase diagram. Because this is extremely, you can see changes to, in resonant frequencies, you can see changes to 10 to the minus 9. So, because this gets tracked in a resonance, it's really, really sharp, you can see very small changes. So that's really good. So you can do qualitative things. The reality is that I know one person that has that name, and they did it for one thing. So what you would do, if or what I want to do in the future, is you can do superficial measurement. You can have a surface sound wave, and you can measure like that. You can measure the superficial. But then what you have to do is to put contacts that are basically like two cones, one against the other, and then in one you send the pulse, and the other you measure, and basically you're measuring time of flight of your sound wave. It's possible to do, but very difficult.
In the very beginning, when you showed the temperature dependence, it seems that this fluctuation or this precursor phase has much more influence on the sound velocity than the transition to this,
Yes.
to the let's say,
To the Skyrmion or to
the magnetic phase.
Indeed, this is the minima you see as. Let me go to the page here. This is a transition that will go to the extrapolation of the paramagnetic as a function of field transition. Is effect you see, and this is the dimension you see there, and this is this little thing is what you see. So what it's telling you partly is that you have a subsystem that are the spins, and they are not the only thing that you have in your
But
system.
if your interpretation would be correct, that means then that, let's say, all the fluctuations are 2 Kelvin above, ahead, and then the spin system acts.
Yeah, we're also seeing that when we put field, these fluctuations are enhanced. You can see this is zero field, this is with field. So the fluctuations are field sensitive. That will tell you that it's also spins are playing an important role.
Do you have data to higher fields?
No, this is the highest we have. We had a really big board cryostat. We were supposed to get a cryostat like a year and a half ago, and we got it last week. So now I have a board that is this size. This is a normal magnet. This is just a split coil normal magnet, and I will be able to go to 1 Tesla. Future thing is I'm making a system to go to PPMS, and then we can have a DC magnet that goes up to 8 Tesla, so we can do it.
May I add one technical question?
Ask it.
When I from time to time I go to high frequencies, and then I have still to use this pulse echo technique.
Yes.
Why can't I use this technique?
Why they? Oh, because
We might like to have this old-fashioned technique.
so the reason is this. Usually you have your sample like this. So you have to have a resonant condition. And whoever has played the triangle in band or has played, let's say, a bell, you play your resonant is doing like that, and then you grab it. And when you grab it, what happens? You kill the resonance. So in a high field or a pulse field, you have a lot of forces, and if your sample is basically loose, it will fly away. And so in pulse fields, there are people at least in Salamos, and I know also in Germany, and for sure in France too. So what they are doing, they're using pulse echo. And that you can glue your sample to something, it can be stay, and you can measure really fast. These
So-
days,
Is there some glue or just press?
this is just touching. You look at it and it falls.
So it's not fixed enough.
No. This is free resonant condition.
And in high fields, it's not fixed enough.
No. And what we did to fix it in the field is we put some alumina hemispheres, so that allows us to have it flat. And then you can make basically a mold or a frame paper that make the sample to stay in the same direction. Because since we have a horizontal field and we have a cubic system, we want to have the 1, 0, 0 in the field. So if we're going to have some sort of lateral thing that puts it in place, it will rotate in the field.
I think more technical discussion.
Okay, we